Today we're going to talk about atomic structure. There are a couple different forces that hold atoms together. There's electromagnetic force and the nuclear force. This first one you've heard of before. It's what you've been learning about since pretty much elementary school, right? It's this idea that opposites attract. There's a positive and a negative side of a magnet, and they will attract each other. This is what keeps the electrons near the nucleus. If the nucleus is positively charged, our electrons that are floating around the outside of the nucleus are all negatively charged. They're not going to fall away because the negative electrons will be attracted to the positive nucleus. The second type of force is a little bit different. It's called the nuclear force. The nuclear force is something that was discovered a little bit later. It also has the name the strong force. Basically, when you have a lot of protons and they're all gathered together in the nucleus, scientists could not explain why the nucleus didn't just fall apart. We know that opposites attract, and therefore positive and positive charges, like charges, should repel each other, but they don't in the case of atoms. They stay together. So this nuclear force, also known as the strong force, is what keeps the nucleus from breaking apart. It is about 100 times stronger than electromagnetic force. And we're going to look at it a little bit more detail in a little bit. You've probably talked about subatomic particles before, but I want to make sure we go over them. First of all, the word subatomic is going to mean smaller than the atom. The first subatomic particle is the nucleus, which contains two subatomic particles called protons and neutrons. Protons have a positive charge, neutrons have a neutral charge. The atom also consists of electrons. Electrons are not part of the nucleus, and they are around the outside with a negative charge. Now, in an atom, most of the atom's mass is right here in the protons and neutrons. Like 99.9% of the atom's mass is held within the nucleus. The atomic number equals the number of protons. This is the defining characteristic of an atom. The number of protons is what tells me what atom I'm working with. In a neutral atom, which we're going to be talking about today, the protons with their positive charge equal the electrons with their negative charge. And the last subatomic particle I want to tell you about is quarks. All right? We're not going to talk about them or test you on them, but quarks are what make up protons and neutrons. They're kind of subatomic particles. Here is a demonstration to how big a proton and neutron are as compared to an electron. If a proton and neutron were this size, and this was the size of the nucleus, the electron would be completely invisible. We would not be able to see it. You can look at this here. If an atom equals the size of 1, the nucleus is about 1/10,000th the size of the atom. A proton is about 1/100th the size of that, and an electron is 1/100 millionth the size of the atom. So electrons are very, very, very tiny, and they're very, 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 very light as compared to protons. Protons and neutrons are about equal in size. Remember, we watched that TED Ed the other day about what size was an atom. I mentioned the quarks, just so you didn't, leave my class never hearing of them. Quarks are the actual components of protons and neutrons. They're what make up the protons and neutrons. There are 6 types of quarks, and they have very adorable names: up quark, down quark, charm quark, strange quark, top quark, and bottom quark. Some scientists think that these quarks actually have characteristics that make different protons have different characteristics, but we're not going to talk about these very much. 3 quarks equal a proton or a neutron, so you might have like 2 ups and a down, or a charm and 2 strange, and that's how that works. This is your periodic table. If you haven't done so already, it is really important that you at least try to get a printed copy of the periodic table if you print nothing else. Um, this number at the top is the atomic number. The atomic number is the number of protons. The number of protons defines an atom. Today, tomorrow, next week, sodium will always have an atomic number of 11 and have 11 protons. That will never change. The next thing is the element symbol. Sometimes the element symbol is not in English, it might be in Latin or Greek or even another language. So you can see here sodium, which you would think would be like SO, has an element symbol of Na. Below that is the element's name. I promise these won't be as foreign to you. You'll start getting used to these, especially ones like sodium. And below that is the average atomic mass. Now, let me be very clear on this. This isn't necessarily what you learned it was in middle school, so keep paying attention. The atomic number, turns out, also equals the number of electrons in a neutral atom, which we're going to be talking about neutral atoms right now. So sodium, when it is neutral, has 11 protons and 11 electrons. And we'll get to neutrons in a second. The mass number, not to be confused with the average atomic mass, is the number of protons plus the number of neutrons. The mass number is always a whole number. It is not on the periodic table. So for sodium, it wouldn't necessarily be 22.99. It might be 23, it might be 24, it might be 22. Let's look at this example here. This is carbon 12. Turns out that carbon 12 is a really common, what we call isotope of carbon, and its mass number is 12. So we know that carbon, by looking at the periodic table, always has 6 protons. So today, tomorrow, next week, carbon will always have 6 protons. That's what defines it as carbon. It's its atomic number. But this example of carbon has a mass of 12. So 6 of that is protons and 6 of that is neutrons. Okay, so protons weigh 1, neutrons weigh 1, and electrons actually weigh 0 for right now. Isotopes are atoms of the same number with different mass numbers. So here's this carbon 12 we were talking about. This is the isotope's nuclear symbol. You're going to see right here, this carbon is the isotope's atomic symbol. This is the mass number right here. This is that carbon 12 that I had written before. And below that is the atomic number. So you can either write it like this, or you can write the hyphen notation, which is carbon-12. I've also seen it written as C-12. Now, isotopes does sound like something fancy, and it turns out that we really only use the word isotopes when we're talking about nuclear chemistry, which is why most people do think it's quite fancy. But every atom on Earth is really an isotope. It's just that we don't really identify them as what isotope they are because usually it's not important to us. Most carbon on planet Earth is carbon 12. We don't call it the isotope carbon 12 because people don't usually care. But isotopes are the word that we use when we're talking about different types of carbon. So take a look at here. We have carbon 12, remember, with its 6 protons, 6 neutrons. And we also have carbon 14. Carbon 14 has 6 protons because carbon has 6 protons today, tomorrow, next week. And carbon 14 also has 8 neutrons, which gives it a total value of 14. You can find the atom's atomic mass by just counting the number of protons and neutrons in the nucleus. Now, why aren't we counting the electrons here? Well, remember, electrons are teeny, 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 tiny, and they're located around the outside of the nucleus. They weigh essentially 1. So carbon 14, you don't have to add the mass of the electrons to it. The number of electrons in a neutral atom will equal the number of protons. Here's an example of hydrogen. Okay, so hydrogen is the smallest element, it's the smallest atom on the periodic table. Here's protium, which is hydrogen 1, deuterium, which is hydrogen 2, and tritium, which is hydrogen 3. Now, these are so common, these isotopes are so common that they've actually given them names, protium, deuterium, and tritium. That's not usually common, but I like to show you these pictures because here's protium, which has just one proton. It's hydrogen 1 with one thing. Here's deuterium with one proton because hydrogen has one proton always, and it has one proton and one neutron. And here's tritium, one proton, two nitrogen, two neutrons. Take a look here at the isotope chlorine 37. Chlorine 37 has to be written like this because if you'll notice on the periodic table, you cannot see chlorine and think, oh, chlorine 35.45. It doesn't work like that. Okay, so chlorine is located over here on the periodic table at number 17. In order for us to know which isotope of chlorine we're talking about, it needs to be followed by a number. So chlorine 37 has an atomic number of 17, and that's because chlorine is number 17 on the periodic table. It has a mass number of 37. That's because of this 37 right here. We do not look at this for the mass number. Chlorine 37 has 17 protons because the number of protons always equals the atomic number, and it has 17 electrons because right now, chlorine 37, we're talking about a neutral atom. The number of neutrons is the atomic number subtracted from the mass number. So if the mass number is 37, in this case of chlorine 37, we subtract 17, which is chlorine's atomic number, and we get a number of neutrons of 20. That's to say there are 20 neutrons plus 17 protons in the nucleus, which has a mass of 37. This is the atomic symbol for chlorine 37. You'll see there it has a 37 and a 17 to represent its mass number and its atomic number.